Lab 3 Black Hole. The purpose of the video today is to estimate the mass of a black hole with the limited information we are provided, which includes momentum and time. Next, using the estimated value of the black hole mass, we want to determine the initial velocity required for a spaceship to successfully lift off a planet and escape the gravitational pull of the black hole. The main result we will learn by the end of this video is 1. Gravitational net force is dependent on the mass of two objects, and 2. We will also learn that initial velocity is dependent on the net force. The main physics ideas that are present in the experiment include momentum, P equals mv, which we will later use to determine net force. Newton's second law, which we usually see in the form force equals mass times acceleration, or force equals delta P over delta T, will now be calculated using a different formula, dP dt. This formula can be decomposed into force parallel plus force perpendicular. In circular motion, force perpendicular points towards the center of the kissing circle, and force parallel points in the direction of momentum. This equation can further be simplified to dP dt times p hat plus p times d p hat over dt. We will also be using the gravitational force equation to determine the mass of the black hole, and we will of course use the velocity update and position update equation to keep track of the location of the system over time. In part 1 of the lab, I want to find the mass of the black hole. I started by inputting my email in the seed to give me a unique star position. The star mass was given as 2 times 10 raised to the 30 kilograms, and delta T was set to 24 hours or 60 seconds times 60 times 24. At the beginning of the while loop, I calculated momentum initial and momentum final by multiplying mass and velocity. Next, I found the change in velocity and momentum by subtracting the final values by the initial values. I then calculated dP dt by dividing delta P over delta T and setting that equal to net force. The next step was to calculate force parallel, and I did this by using the first part of the formula I showed earlier, dP over dt times p hat. The norm function in VPython finds a unit vector, so I multiplied this value by the magnitude of dP dt to get force parallel. Since we already calculated net force earlier in the code, I simply subtracted net force by force parallel to get force perpendicular, and to find the mass of a black hole, I rearranged Newton's law of universal gravitation to find one of the masses. After running this code, I found that Fnet was 7.68 times 10 raised to the 28 newtons. The black hole mass, which was calculated by taking the average of all the masses, turned out to be 6.22 times 10 raised to the 33 kilograms. The initial conditions in the experiment were the black hole at position 000 meters and the star mass was 2 times 10 raised to 30 kilograms. The system was a star and the surroundings was a black hole. In part 2 of the lab, I set the black hole mass to the value I calculated previously. I set the max time to 3 hours to get a better picture of the orbit, and I found the initial speed to be -5 times 10 raised to the 7 meters per second in the x direction, and 3 times 10 raised to the 6 meters per second in the y direction. In the while loop, I found the net force on the planet by adding the force of black hole on planet and the force of the ship on planet. I did this by calculating the relative position vector and using Newton's law of universal gravitation to find net force. Like before, I used the norm function to find all unit vectors and the mag2 function to find the magnitude squared. I repeat this process to find the net force on the spaceship. Next, I update the position and velocity of the spaceship and planet using the forces I calculated. These final formulas is what allowed me to approximate the initial velocity I needed to escape the black hole. After running this code, I found the initial conditions to be the black hole at position 000 meters and ship velocity to be -5 times 10 raised to the 7th, 3 times 10 raised to the 6th, 0 meters per second in a vector form. The system was a ship while the surroundings included the black hole and the planet. So what is the difference between the rate of change of momentum and net force? We used them interchangeably in the code, so why do they have different names? By Newton's second law, these two values are the same but can be interpreted differently. Change in momentum is calculated by relating final and initial momentum over a period of time, while net force is assumed to be equivalent. So what if we wanted to orbit the black hole instead of escaping it? By shrinking the x-component magnitude, the spaceship had more curvature, and I was successfully able to orbit the black hole. This is because the x-component is force perpendicular, which points towards the center of the kissing circle. By shrinking the radius of the x value, I was able to get a more curved path. Alternatively, if I were to make the radius larger, I would get a straighter path. In conclusion, the mass of a black hole was calculated by manipulating Newton's law of universal gravitation. The black hole mass was then used to find the initial velocity for the spaceship. Some potential sources of error in my code include 1. The mass of a black hole was an average value, not an exact value, so my data could have been skewed. And 2. The ship's initial velocity was a possible answer, but not necessarily the best answer.